In the vast cosmic ocean that surrounds our solar system, humanity has become accustomed to a certain predictability. Comets arrive on schedule, asteroids follow their ordained paths, and the planets trace their ancient orbits with clockwork precision. But every so often, the universe reminds us that we are not alone in this corner of the galaxy, that our solar system is not an island, but rather a waypoint along routes traveled by objects from distant stars. The discovery of the third confirmed interstellar visitor has sent ripples through the astronomical community, reopening questions we thought we had begun to answer and raising new ones we never thought to ask. Unlike its famous predecessors, One-Eye Oumuamua and Two-Eye Borisov, this latest cosmic wanderer has exhibited behavior so peculiar, so utterly unprecedented, that it has forced scientists to reconsider not just what we know about interstellar objects, but what it means for something to be interstellar at all. To understand the significance of our third interstellar visitor, we must first revisit the astronomical earthquakes caused by its predecessors. For centuries, astronomers had theorized that objects from other star systems must occasionally pass through our own, but proving this hypothesis was another matter entirely. The velocities required, the vast distances involved, and the sheer difficulty of distinguishing an interstellar interloper from the countless native objects in our solar system made detection seem almost impossible. Then came October 2017, and everything changed. The Pan-STARRS 1 telescope in Hawaii detected an object moving through the inner solar system at an astonishing velocity. Initially catalogued as a comet, then an asteroid, the object soon revealed itself to be neither, or rather, something entirely outside our existing classification schemes. Designated One-Eye Oumuamua, Hawaiian for scout, or messenger from afar arriving first, this cigar-shaped visitor was traveling at speeds that could only mean one thing. It had originated from beyond our sun's gravitational domain. Oumuamua's discovery was revolutionary not because of what we learned about it. In truth, we learned frustratingly little, but because it proved that interstellar objects could be detected at all. The object's extreme elongation, its peculiar acceleration that couldn't be fully explained by solar radiation pressure or outgassing, and its tumbling rotation made it a subject of intense speculation. Was it a shard of a shattered planet? A nitrogen iceberg from a Pluto-like world? Or, as a few bold researchers suggested, could it be something artificial? Before the astronomical community could fully process the implications of Oumuamua, a second interstellar visitor arrived. Discovered in August 2019 by amateur astronomer Gennady Borisov, Two-Eye Borisov was in many ways Oumuamua's opposite. Where Oumuamua had been enigmatic and alien, Borisov was refreshingly familiar. It looked like a comet, behaved like a comet, and provided scientists with the first opportunity to study an interstellar object in detail over an extended period. Spectroscopic analysis revealed that Borisov's composition wasn't dramatically different from comets in our own solar system. It possessed a familiar coma of gas and dust, a tail shaped by solar radiation, and chemical signatures that suggested a formation environment not unlike the outer reaches of our own stellar nursery. If Oumuamua had been a cryptic riddle, Borisov was a reassuring confirmation that at least some aspects of planetary formation were universal. Together, these two objects established a baseline. They gave us data points, references, a framework for understanding what to expect from interstellar visitors. They also gave us false confidence that we were beginning to understand the nature of these cosmic wanderers. The third visitor would shatter that confidence completely. The detection of what we now call the third interstellar visitor, tentatively designated 3-Eye name pending, came not from a single observatory but from a coordinated network of sky surveys specifically designed to catch these fleeting visitors. The Vera C. Rubin Observatory's legacy survey of space and time, working in conjunction with next-generation detection algorithms trained on the signatures of Oumuamua and Borisov, flagged the object in the early hours of a spring morning. Initial observations suggested nothing particularly unusual. The object's trajectory clearly indicated an origin beyond our solar system, with a hyperbolic orbit that would carry it through the inner solar system and back out into interstellar space. Its velocity, while high, fell within the expected range for objects ejected from other stellar systems. Size estimates placed it somewhere between its two predecessors, larger than Oumuamua's estimated 400 meters in length, but smaller than Borisov's roughly kilometer-wide nucleus. The first hint that something was deeply wrong came from spectroscopic analysis. Unlike Borisov, which had exhibited the expected signatures of water ice, carbon dioxide, and organic compounds, and unlike Oumuamua, which had shown virtually no spectral features at all, This new visitor displayed an absorption spectrum unlike anything in our catalogs. There were familiar elements, iron, silicon, carbon, but in ratios that made no geochemical sense. More disturbing were absorption lines that didn't correspond to any known molecule or mineral. Absorption features at wavelengths never before observed in natural materials. Extremely high abundance of heavy elements inconsistent with standard stellar nucleosynthesis, temperature variable spectral signatures suggesting active processes rather than passive reflection. Periodic changes in spectral features on a 4.7-hour cycle. At first, we thought our instruments were malfunctioning, recalls Dr. Sarah Chen, lead researcher on the observational team. We ran calibrations, checked for contamination, even wondered if we were seeing atmospheric interference. But observation after observation confirmed it. Whatever this object is made of, it's not like anything we've seen before, not in our solar system, not in meteorites, not even in the spectra of exoplanets or protoplanetary disks. If the spectroscopic anomalies were merely perplexing, the object's behavior in transit has been downright unsettling. Unlike Oumuamua, which exhibited a slight non-gravitational acceleration, or Borisov, which followed a trajectory consistent with standard cometary outgassing, the third visitor has demonstrated changes in velocity that defy conventional explanation. The object appears to be accelerating and decelerating in patterns that correlate with no known physical mechanism. These aren't the gentle, continuous accelerations produced by comet jets or the Yarkovsky effect, whereby absorbed and re-radiated sunlight can gradually alter an object's orbit. Instead, they're discrete, almost pulsed changes that occur with apparent periodicity. Even more bizarrely, these velocity changes don't always occur in the direction one would expect from rocket-like outgassing. Sometimes the object accelerates toward the sun when it should be accelerating away, or vice versa. Several theoretical frameworks have been proposed to explain this behavior, each more exotic than the last. Some researchers have suggested the object might be a fragment of a binary system whose components are still gravitationally bound, creating periodic tidal accelerations. Others have proposed that internal radioactive decay might be venting material in controlled bursts. A few have even revived the possibility of magnetic interactions with the solar wind, though calculations suggest this would require magnetic fields orders of magnitude stronger than those of typical asteroids. None of these explanations fully fit the data. And that's when scientists began to entertain more radical possibilities. Perhaps the most visually arresting aspect of the third interstellar visitor is its appearance. While Oumuamua was never directly imaged with sufficient resolution to discern its shape, its elongated form was inferred from light curve variations, and Borisov appeared as a fuzzy blob typical of active comets. Advanced adaptive optics systems and space-based telescopes have captured remarkably detailed images of our latest visitor. The object is neither the cigar shape of Oumuamua nor the rounded nucleus of Borisov. Instead, it appears to have a highly irregular, almost fractured appearance, like a piece of shattered glass or crystalline structure. High-resolution imaging reveals what appear to be flat, reflective surfaces at odd angles to one another, creating a geometric complexity that seems at odds with natural erosive or accretionary processes. It looked less like an object shaped by the patient hand of natural forces and more like something that had been assembled, then shattered, then partially reassembled according to alien geometric principles. The object's rotation is equally peculiar. While many asteroids exhibit complex rotation states, tumbling along multiple axes rather than spinning smoothly like a top, the third visitor's rotation appears almost choreographed. It executes what mathematicians call a non-principal axis rotation, but with such precision that some researchers have suggested it might actually be intentional stabilization rather than chaotic tumbling. Most intriguingly, certain facets of the object seem to be highly reflective, far more so than would be expected from rocky or icy surfaces. During specific points in its rotation, the object's brightness spikes dramatically, creating a light curve that resembles less a natural asteroid and more a disco ball catching the sun. Spectral analysis during these bright phases has revealed something even more unusual. The reflected light appears to be partially polarized in ways that don't match solar radiation. Perhaps inevitably, given the object's anomalous nature, the question of artificial origin has arisen. While the scientific community remains appropriately skeptical, several research groups have quietly begun conducting SETI-style observations of the visitor, searching for any indication of electromagnetic emissions that might suggest technology rather than geology. So far, these searches have revealed nothing conclusive, but they have detected something odd. The object appears to emit weak radio signals at several frequencies, though whether these are natural plasma interactions, electrical discharges from surface materials, or something else entirely remains unclear. The signals are irregular and lack the structured patterns that might indicate intelligence, but their very presence is unusual for an object of this type. Dr. James Morrison, a radio astronomer involved in the monitoring efforts, urges caution in interpretation. We're seeing electromagnetic emissions, yes, but jumping to conclusions about artificial origins would be premature. Comets emit radio waves. Asteroids with certain mineral compositions can generate electric fields when exposed to solar wind. Lightning has been detected on Venus, Jupiter, even in Earth's thunderstorms. What we're seeing could be any number of natural phenomena we simply haven't encountered in this specific combination before. Nevertheless, the possibility has captured public imagination in a way that even Oumuamua's mysterious nature did not. The third visitor has become a cultural phenomenon, inspiring everything from conspiracy theories to science fiction narratives, from serious academic conferences to endless internet speculation. As observing opportunities have accumulated, scientists have built an increasingly detailed and increasingly puzzling picture of what the third interstellar visitor might be made of. The spectroscopic data, while anomalous, has been subjected to every analytical technique available to modern astronomy, and the results paint a picture of an object that challenges our understanding of material science. The most comprehensive analysis suggests that the object's surface contains an unusually high concentration of refractory metals, elements like tungsten, rhenium, and osmium that typically remain solid even at extremely high temperatures. These elements are rare even in our solar system, typically concentrated in the cores of differentiated bodies rather than exposed on surfaces. Their presence in such abundance suggests either a formation environment radically different from anything in our stellar neighborhood, or that this object is a fragment of something much larger and more complex. Discovery plus 3 days. Initial spectroscopy reveals unusual composition. First hypothesis, contaminated data. Discovery plus 2 weeks. Non-gravitational acceleration detected. Multiple observatories confirm anomalous trajectory changes. Discovery na 1 month. High-resolution imaging reveals geometric structure. Public interest intensifies dramatically. Discovery plus 6 weeks radio emissions detected. SETI protocols initiated by multiple research groups. Ongoing continuous monitoring as object traverses inner solar system. Every observation raises new questions. Equally puzzling is evidence of what appears to be layered structure. By analyzing how the object's spectrum changes as different facets rotate into view, researchers have determined that the surface composition isn't uniform. Instead, there seem to be distinct regions or layers with different chemical signatures, almost like geological strata, except the boundaries are too sharp and the compositions too distinct to have formed through gradual accretion or differentiation. It's as if we're seeing an object that has been through multiple formation processes, explains Dr. Maria Rodriguez, a cosmochemist specializing in primitive materials. We see signatures that might indicate formation in a hot, high-pressure environment, perhaps near a star. But we also see materials that could only have formed in the cold vacuum of deep space. And we see organizational complexity, layers, boundaries, structures that don't match any natural aggregation process we know of. One of the most fundamental questions about any interstellar object is, where did it come from? For Oumuamua, despite extensive analysis, we were never able to definitively identify a parent star system. The object's trajectory, when traced backward through space and time, didn't point clearly to any nearby stellar system. Given the sun's motion through the galaxy and the object's own velocity, it could have been wandering interstellar space for millions of years, its origin lost to the chaos of galactic dynamics. For Borisov, the situation was somewhat clearer. While no single parent star could be identified with certainty, the object's velocity and trajectory were consistent with ejection from a stellar system relatively recently, perhaps within the last few million years. Its composition suggested formation in an environment similar to our own solar system's outer regions, making it a refugee from a planetary system much like ours. The third visitor presents a different puzzle entirely. When astronomers calculate its trajectory backward through the galaxy, they arrive at a disturbing conclusion. The object's path doesn't intersect with any known star system within the last 100 million years. Its velocity is too high, its trajectory too vertical relative to the galactic plane, to have been casually ejected from a nearby stellar neighbor. This suggests several possibilities, each more unsettling than the last. Perhaps the object was accelerated to its current velocity by some catastrophic event, a close encounter with a stellar mass black hole, perhaps, or ejection from a supernova remnant. Perhaps it originated in a globular cluster or some other dense stellar environment where gravitational interactions routinely fling objects to extreme velocities. Or perhaps it has been traveling through interstellar space for an inconceivably long time, a wanderer from an era when the galaxy structure was entirely different. The third interstellar visitor has forced astronomers to confront the limitations of their models in ways that previous discoveries did not. Before Oumuamua, the consensus model suggested that interstellar objects should be primarily icy bodies, failed comets and scattered disk objects ejected during planetary system formation. Oumuamua challenged this by being rocky or at least lacking obvious ice. Borisov seemed to confirm the original model by being cometary. Now, the third visitor has shattered any emerging consensus entirely. The existence of objects with such unusual compositions, trajectories, and behaviors suggests that our understanding of planetary system formation and evolution is incomplete. If interstellar space is populated by objects that don't fit into our neat categories of asteroid or comet, what does that mean for the diversity of planetary systems throughout the galaxy? Some researchers have begun to advocate for an entirely new framework for thinking about interstellar objects. Rather than categorizing them based on composition or appearance, categories derived from objects in our own solar system, perhaps we should classify them by origin and history. Was an object formed in a protoplanetary disk, ejected from a mature planetary system? Created in a stellar collision or merger? Each formation pathway could produce objects with radically different properties. We are, in essence, seeing archaeological artifacts from planetary systems we can never directly observe. Frozen snapshots of processes that occurred billions of years ago, light years away. The third visitor has also reignited debates about the frequency of interstellar objects passing through our solar system. Based on the detection of 3 such objects in less than a decade, statistical models suggest that at any given time there might be several interstellar visitors within the orbit of Neptune. Most would be too small or too distant to detect with current technology, but they're there. A constant rain of cosmic refugees passing silently through our neighborhood. This realization has profound implications for planetary science. If interstellar objects are common, they represent a mechanism for transferring material and potentially even life between stellar systems. Panspermia, the hypothesis that life might be spread throughout the universe via natural processes, becomes more plausible if we acknowledge a galaxy-wide exchange of material via interstellar objects. Every star system might receive regular deliveries of prebiotic chemistry or even viable organisms from other worlds. One of the most frustrating aspects of studying interstellar visitors is their ephemeral nature. These objects enter our detection range for a brief window, sometimes just weeks or months, before racing back out into the depths of space, never to return. With Oumuamua, we largely missed our opportunity for detailed study, detecting it only as it was already leaving the inner solar system. With Borisov, we were better prepared but still constrained by the object's trajectory and the capabilities of our instruments. For the third visitor, the astronomical community is determined not to squander the opportunity. An unprecedented coordinated observing campaign is underway, involving virtually every major telescope on Earth and several space-based observatories. The object's trajectory has been calculated with exquisite precision, allowing astronomers to plan observations months in advance, maximizing every possible moment of study. There are even discussions, though still purely theoretical, of mounting a rapid response mission to intercept the object. Current rocket technology wouldn't allow us to match velocities with an interstellar visitor and return samples to Earth, but a high-speed flyby might be possible. Engineers have sketched out scenarios involving trajectories that would bring a spacecraft close enough to capture high-resolution images, collect dust particles from the object's vicinity, and conduct in-situ measurements that could answer some of the most pressing questions about its composition and structure. The European Space Agency has announced preliminary studies for a mission concept called Comet Interceptor, originally designed to study pristine comets but adaptable to interstellar targets. NASA has quietly begun internal discussions about repurposing existing missions or fast-tracking new ones. Private space companies have also expressed interest, seeing in these cosmic visitors not just scientific targets, but potential mining opportunities, though the economics and ethics of extracting resources from interstellar objects remain deeply controversial. Beyond the immediate puzzle of the third visitor's nature, These objects offer unprecedented windows into stellar systems we could never reach. Every interstellar visitor is a messenger carrying information about conditions, processes, and events from distant corners of our galaxy. By studying their compositions, we learn about the chemical evolution of other stars. By analyzing their structures, we discover how planetary systems form and evolve under different conditions. By tracking their trajectories, we map the unseen gravitational landscape of our galactic neighborhood. The third visitor, despite, or perhaps because of, its anomalous nature, has the potential to be our most informative interstellar sample yet. Its unusual composition might reveal formation processes we've never considered. Its trajectory could point us toward previously unknown stellar populations or galactic structures. Even its mysteries, if they remain unsolved, will define the boundaries of our ignorance and suggest directions for future research. Dr. Robert Chen, director of the Small Bodies Division at the International Astronomical Union, frames the significance this way. Every interstellar object is like receiving a message in a bottle from a distant shore. We don't know who sent it, we don't know when it was set adrift, and we can barely read the message. But each one tells us that the shores are real, that the ocean is vast, and that we are part of something much larger than we ever imagined. As observations continue and data accumulates, it becomes increasingly clear that the third interstellar visitor may not yield its secrets easily. Unlike scientific problems that can be solved with enough data and analysis, this object seems to resist classification, defying our attempts to fit it into familiar categories. Perhaps that's the most important lesson it has to teach us. Modern astronomy has achieved remarkable things. We've mapped the cosmic microwave background, detected gravitational waves, imaged black holes, and discovered thousands of exoplanets. These achievements might lead one to conclude that the universe, while vast, is ultimately comprehensible, that given enough time and technology, we can understand anything we encounter. The third interstellar visitor suggests otherwise. It reminds us that the universe is still capable of surprise, that our models and theories are approximations rather than absolute truths, and that out there in the cosmic dark, there are phenomena we haven't yet imagined. This is not a defeat for science, but an invitation, a reminder that the work of understanding the universe is never finished, that each answer generates new questions, and that mystery is not the absence of knowledge, but the frontier of discovery. Continuous spectroscopic monitoring to track composition changes as the object traverses different regions of the solar system. High-resolution imaging to map surface features and search for active processes. Radio and infrared observations to detect any thermal or electromagnetic emissions. Trajectory refinement to determine if non-gravitational accelerations follow. Predictable patterns. Comparative analysis with meteorite samples and laboratory analogs to identify possible formation mechanisms. Theoretical modeling of extreme formation environments that might produce such unusual characteristics. As this article goes to publication, the third interstellar visitor continues its journey through our solar system, drawing ever closer to perihelion, its closest approach to the Sun. Telescopes around the world track its progress, capturing every photon of reflected sunlight, analyzing every subtle change in spectrum or trajectory. The data streams in, petabytes of information that will take years to fully analyze, containing secrets we haven't yet learned to read. In a few months, the object will round the Sun and begin its long journey back to the stars. The intensity of observation will gradually decrease as it becomes fainter and more distant, until finally it fades below the detection threshold of even our most powerful instruments. It will rejoin the darkness between stars, carrying its mysteries back into the void from which it came. But it will leave behind something invaluable. Questions. Questions about planetary formation, stellar evolution, galactic dynamics, and our place in the cosmic order. Questions about what else might be out there, traveling the vast spaces between stars. Questions about the limits of our knowledge and the vastness of what we don't yet understand. The third interstellar visitor has reminded us that we live in a universe that is not just vast in space, but infinite in possibility. Every answer we find generates new mysteries, every solved puzzle reveals deeper questions, and every visitor from beyond our stars brings with it the promise and challenge of the unknown. The road ahead. The discoveries precipitated by the third interstellar visitor are already shaping the future of astronomy. Funding agencies are prioritizing next-generation sky surveys specifically designed to detect these cosmic wanderers earlier and more reliably. The Rubin Observatory survey, when fully operational, is expected to detect perhaps dozens of interstellar objects per year, transforming what was once an astronomical rarity into a regular occurrence. New instruments are being designed with interstellar visitors specifically in mind. Rapid response observation networks that can redirect multiple telescopes to a new target within hours. Spectroscopic systems optimized for the unique challenges these objects present. Even spacecraft mission concepts that could be launched on short notice to intercept and study these visitors up close. The theoretical work prompted by these objects is equally vigorous. Astrophysicists are developing new models of planetary system evolution that account for the diversity we're observing. Astrochemists are exploring exotic formation pathways that might produce the unusual compositions we're detecting. Dynamicists are refining our understanding of how objects can be ejected from their parent systems and what that tells us about planetary architectures throughout the galaxy. Perhaps most significantly, the third visitor has reinvigorated public interest in astronomy in ways that even the most spectacular telescope images sometimes fail to achieve. There's something uniquely captivating about the idea of objects from other star systems passing through our cosmic neighborhood. Tangible proof that we're part of a larger galactic community, even if our neighbors are too distant to visit directly. In seeking to understand these cosmic visitors, we are really seeking to understand ourselves, our origins, our context, our place in the grand tapestry of cosmic evolution. The third interstellar visitor will eventually fade from our telescopes and likely from public consciousness. Future visitors will bring their own mysteries and capture their own headlines. But the questions this object has raised will persist, driving research and inspiring curiosity for generations to come. In the end, that may be its greatest gift, not answers, but the reminder that the universe still has the power to surprise us, to challenge us, to inspire wonder. As we watch this enigmatic object continue its journey through our solar system and back out to the stars, we're reminded of a fundamental truth about science and exploration. The most valuable discoveries are not always those that confirm our theories, but those that confound them. The third interstellar visitor has given us exactly that: a puzzle we cannot yet solve, a mystery we cannot yet unravel, and a clear demonstration that the universe is more strange, more diverse, and more wonderful than we ever imagined. And somewhere out there, in the dark spaces between the stars, more visitors are on their way, carrying with them new mysteries, new challenges, and new opportunities to expand the boundaries of human knowledge. We have only to watch, to wonder, and to wait for the next message from beyond our stars.